Okay, YouTube, in this last video in my module over the normal distribution or normally distributed data, basically what we're going to confront is that not all distributions are normal. And that says here, for instance, consider the histograms that we see below. And so you'll notice that the first histogram, it looks approximately normal. As a matter of fact, very, very normal. We could model this very well using our bell-shaped curve. But you'll notice also that with this bell-shaped curve, that the mean is in the middle. And so we would say that this right here would look like a normal distribution, but we can identify the normal distribution because it's very, very bell-shaped and there's symmetry, okay, symmetry. With respect to, an asymmetrical bell shape, you can see that if we were to have an instance here where the median was actually higher than the mean, which is usually in the middle, and we say also if the median is lower than the mean, then what we get is referred to as a skew, okay? And so we could say that these maybe looked like they were bell-shaped, but they were twisted one way or another. You'll notice that because they are twisted or skewed one way or another, that we say that the histogram does not have a normal distribution. And so in a normal distribution, one key characteristic is that the mean and the median are basically the same thing-ish, but not spread far apart from one another, and also that it's not kind of a skewed bell. So when we look at skewed left versus skewed right, one thing that I will tell you is this. You can see how there's this dotted line kind of drawn over here. It looks like a bell shape, but each of these bells have a tail. And so I would say the tail is on the right this time. Over here, the tail is on the left. And the tail is usually identified as being not the abrupt end of this, the really steep end, but the long and drawn out end that also contains a side with a mean. So we can see that normally distributed things basically are approximately symmetrical about the mean. And so up here, basically, I want to do is have us determine whether or not each histogram has a normal distribution. So when we look at, say, the heights of women in the United States ages, in their 20s, we could see that their height, as their height gets bigger and bigger, the relative frequency gets, I guess I don't want to say bigger and bigger. The average height would be somewhere probably in here in the middle. And as we move away to the very, very shorter people and the taller people, we can see that the relative frequency starts to drop off here, or the percentage of the population that has that height. So I would say that because we could say that this is approximately symmetrical here, it's approximately bell-shaped, and that the average would be somewhere in the middle, then this would be a normally distributed thing. So it's normally distributed. Okay, normally distributed. When we look at this next one here, you can see that it does kind of go up and then down, but it definitely has a tail here. And so we'd say that this is a right skewed thing. First of all, right skewed because the tail exists on the right. And we say not normally distributed. Not normally distributed. So looking at this last two, how would you judge them? Which one of these would be our normally distributed one? I'm hoping you would say letter B, because you could see that B is a bit more symmetrical here, even though it's not perfectly symmetrical, whereas in A here we get this skew right here. So we'd say it's not normally distributed here. Not normally distributed. It's not a normal distribution. But this is more of a normal distribution here. And so it's going to be imperative that we can distribution. Identify data sets that are normally distributed, because if we can, then we can make the assumption that the population might look like this, and based upon our sample data, start collecting or calculating probabilities that certain events would occur, given our perfectly normally distributed curve. Cheers.